Okay, let's take a look at example 2. So example 2 says given 1 plus x squared plus x cubed plus ... equals 1 over 1 minus x, which makes sense, right? Because a sub 1 is 1 and we're multiplying by x every time. It says find a power series to represent 1 over 1 minus x squared. That's a little weird, okay? However, if you kind of think of the sum of this first one, right, as 1 minus x to the negative first power, right? Can you see a way we can take 1 minus x to the negative first power and maybe turn it into 1 minus x to the negative second power, right? Is there a relationship between these two? Remember, this is calculus after all, right? And what's the thing we love doing in calculus a lot? That's right, where you can take a derivative, okay? So here's kind of one way of thinking about this, right? I'm going to take a look at this power series right here, and I'm going to think of it as a function, right? I'm going to say f of x is equal to 1 plus x squared plus x cubed plus ... And we know, right, that for this we can use our sum of an infinite geometric series formula, and we can say it equals to 1 over 1 minus x. Now again, this only works for r being, r has to be between negative 1 and 1, so x has a specific interval in order for all this to work. Okay, so if I take this right here and I go, all right, cool, what if I took the derivative of this whole thing with respect to x, right? That would give me f prime of x, and now each individual term would be now 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus ... right? And eventually, right, 1 minus x to the negative first, take the derivative, use the chain rule, right? You would get 1 over 1 minus x squared. If I can get this to move over, there we go. Okay, good, right? So now here we do have a series that can represent 1 over 1 minus x squared. So the last thing I'm going to do is I'm just going to rewrite this in sigma notation, right? So here's my sigma, right? And I'll say starting at n is equal to 0, right? Of going all the way up to infinity, right? So what was this one that I started with, right? Well, I can just say this was x to the n, right? Starting at 0. And so what did I do with it? I took its derivative. So what's the derivative of x to the n? N times x to the n minus 1, right? That is going to equal 1 over 1 minus x squared. Okay, right? So here is a power series, right, that I can use to represent 1 over 1 minus x squared. Okay, example 3, very similar. Okay, given same function from group problem 1, right? So we have f of x equals this series, right? 0 to infinity, 5 times x plus 4 over 3 all to the n. It says find f prime of x and its interval of convergence. Okay, so the interval of convergence part, that's the same as group problem 1, right? Because it's the interval of convergence for f, okay? So I'm not going to do that, okay? Let's just focus on finding f prime. So let's go back real quick to group problem 1, okay? And so remember, we found the sum for this series, right? And we said it was negative 15 over x plus 1, okay? So I can say, right, that if I take this series, right? So I'm going to copy all of these terms, okay? So if f of x is equal to these terms added together, right, I will get the sum that I got, again, from group problem 1, negative 15 over x plus 1. Right? This is what f of x equals. So to find f prime of x, well, all I have to do is take the derivative of this then, right? F prime of x is just going to be, right, okay, well, let's go ahead and do the, what do we got here? This little chain rule, right, action here, right? Well, x plus 1, its derivative is just 1, so this works out nicely, right? I'll get 15 over quantity x plus 1 squared. And that's my answer. Okay, so we already did the legwork in group problem 1 for this example, right? If we didn't know what the sum was equal to, right, we would have to do that, right, just like we did back here, right, going through the work a sub 1 over 1 minus r, right, doing all of that, right, to get negative 15 over x plus 1 and then take its derivative. Okay, good. Okay, and again, the interval of convergence is the same as group problem 1, so we're going to move on from that. Okay, all right, let's go down to our last one, example 4. So given f of x is this infinite series, negative 1 to the n power times x to the 2n, it says find the integral of little f of x dx, which is going to be called big f of x, okay, and the interval of convergence on this one, all right? So this one's a little tricky, okay, but let's write this out, and let's write out some of the terms in this series so we can see what's going on. So f of x is this series starting at 0, going to infinity of negative 1 to the n, x to the 2n power, right? So what are some of the terms here, right? So if I plug in 0, I'm going to get positive 1, right? If I plug in 1, I'm going to get negative x squared. If I plug in 2, I'll get positive x to the 4th. If I plug in 3, I'll get negative x to the 6th, and it's going to go on and on like that, okay? So what is this going to be equal to, right? Well, let's think of it like any other geometric series, right? A sub 1 is going to be 1, and then r, right? So what am I multiplying by to get the next term? Be careful on this one because we've got the flip-flopping of the signs. It is actually negative x squared is what you're multiplying by, okay? So this is going to equal 1 over 1 minus the quantity negative x squared, which is 1 over 1 plus x squared. Okay, so this is what f of x is, right? Little f of x, right? It is 1 over 1 plus x squared, right? Based on taking this geometric series, right, and using our sum formula, okay? But here's the thing, we don't really want to know what little f of x is, we want to know what big f of x is, right? So what if I were to take the integral? Okay, now you're going to have to forgive me, we're not putting dx's in all of this, right? But if I were to take the integral of this, right, it would mean taking the integral of this sum, right, which would mean taking the integral of what we have at the end there, 1 over 1 plus x squared. But it would also mean taking the integral of each of these terms separately, right? The 1, the negative x squared, the plus x to the 4th, the minus x to the 6th, etc., right? So if I were to do that, right, in order to get big f of x, right, what would that be, right? Well, let's think about it, okay? How can I take an integral, right? Well, luckily there is a power rule, right? So what that means here is that big f of x, writing it in sigma notation, would be n is equaling to 0, going to infinity, right? Now the negative 1 to the n, you can think of that as kind of like a constant, right? So I'll leave that there. So what's going to happen with x to the 2n, right? What do we do when we have a power, right? Well, we add 1 to that power. So it's x to the 2n plus 1. But then remember, we also have to divide by our new exponent. So it's all over 2n plus 1, right? So this is big f of x in sigma notation. And now, if you want, you can start plugging 0, 1, 2, 3, etc. into this, right? Or you can just take the antiderivative of these terms, right? Which would give us x negative 1/3 x cubed plus 1/5 x to the 5th. Whoops, that should be a minus 1/7 x to the 7th plus et cetera, right? And another way of thinking about it then is, well, what is the antiderivative of 1 over 1 plus x squared? And now, hopefully, alarm bells are going off, right? Because this is a top 20 integral. And, feel free to pause the video, right? And look back at that top 20 integral list. It's been a while since we've kind of like looked through it or had a quiz on it, right? What is the antiderivative here, right? It is our old friend, the arctangent of x. Okay, so this is kind of cool, right? This series is equal to the arctangent of x. That's kind of wild, right? X minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th, right, et cetera, is actually going to give you arctangent of x. That's pretty cool, okay? But remember, all of this is only true, right, if we're thinking geometric, r has to be, right, between -1 and 1, right? So if I think of it as, again, absolute value of r is less than 1, which means the absolute value of -x squared is less than 1. But here's some good news, right? Absolute value of -x squared is the same as the absolute value of x squared, right? Because the whole point of the absolute value is to get rid of that negative. So x squared has to be, absolute value of x squared, well, we don't even really need the absolute value, right? And so if we kind of take the square root here, right, we actually still end up with -1 to 1. That is the interval of convergence. Okay, so some unique uses here with these power series, okay, and this is going to bring us into next week's lesson on a very fun topic called Taylor series. So I'll see you all next time for that.